There we go. All right. Apologies for the delay there, but I think we're ready to get started. I've heard an introduction, but I'm afraid that I didn't understand all of it, so I'm just going to do the introduction again. I'm Kristof. I'm here to talk about IF Bridge performance, and we'll get right into it. We'll start with the usual shameless self-promotion. I've already mentioned my name. You can reach me at kp@freebsd.org, which means that I am a FreeBSD committer. One of the things I do in FreeBSD is I maintain one of our firewalls called BF, which we obtained from OpenBSD. We added a couple of nice features to that in FreeBSD, but well, that's a different talk. Professionally, I do a lot of embedded projects, many of them on Linux. Recently, I've professionally also been doing a lot of RISC-V, and been having quite a lot of fun with that. I would thoroughly recommend that you all go out and buy a RISC-V board. I say I would recommend because it turns out that it's kind of hard to get your hands on hardware, but if you can, you totally should. It's fun architecture. I was palmed into joining the RWLock Foundation board a few years ago, which means that I'm involved in organizing, well, the European BSD conference, which was supposed to happen in September in Vienna this year, but then, well, the obvious. Anyone interested in BSD should totally join us in Vienna in 2021, September 2021, precise dates to be confirmed. And finally, I'm also a FreeBSD Journal editorial board member, which sounds very grandiose, but basically means that I badger people into writing for the FreeBSD Journal. So if anyone has anything they want to share in the FreeBSD Journal, don't hesitate to reach out. For those of you who don't know, the FreeBSD Journal is a bi-monthly, every other month publication about FreeBSD, and it's free. So you can get that on the website of the FreeBSD Foundation, I believe. If you just search for FreeBSD Journal, you're going to find it, and it has a bunch of interesting articles, and also one or two by me. While I'm doing the shameless promotion of things, I should also promote the FreeBSD Foundation because they generously supported this work. The FreeBSD Foundation is the foundation that supports FreeBSD. You may have heard about it already today, but, well, I didn't, so I'm afraid I'm going to repeat it here. The FreeBSD Foundation supports the FreeBSD project, basically. That means they do things like paying or sponsoring conferences. They also sponsor certain projects that will help FreeBSD evolve and improve, one of which was my bridge project, but they also sponsor a whole bunch of other projects. They also tend to do things like present a legal entity if a developer happens to need to sign non-disclosure agreements or things like that. They can always use money, so if you have some money and you don't need it, the FreeBSD Foundation would love to help you with that problem. Moving on anyway, we're here to talk about bridges, connecting one side of the river to the other side. And, no, wait, that's the wrong sort of bridge. The sort of bridge we're talking about here today is this one. Switches. FreeBSD as an operating system can be a bridge. So you can take your very expensive server machine with 4 network interfaces and turn it into kind of a not very good switch. Because even after all of this work, your cheap hardware switch is probably going to be faster and not make as much noise and not need as much power. So why would you want to do this anyway? Well, we'll get into why you would want to do this after we talk about the sorts of things that it can do. You can take a two or more Ethernet interfaces and link them together, turn them into a single broadcast domain, which means you can pass packets from A to B and also from B to A. Important feature, that one. It also supports things like the spanning tree protocol. There is a wonderful poem that explains how spanning tree works. You should all look it up and memorize it. I have failed to memorize it, I have failed to look it up, but I know it exists and I thoroughly recommend it to everyone. We also support port mirroring, which means you can take a port out of your bridge and say all of the traffic that passes over the bridge needs to be copied out of that port. Why would you want to do this? Well, it's useful when you're debugging things. You could take, say, an embedded board that you're debugging that you know connects to the internet and does strange and mysterious things. You can plug it into your computer, bridge it to your LAN interface, and then monitor traffic on that bridge, see what happens. Because this is a bridge, it's entirely transparent to that device, and you can get good monitoring done that way. More realistic use cases, we've covered debugging. I think the primary use case for bridging is when you're doing things like VM hosting, be that with a Beehive full virtual machine or with FreeBSD's VNet jails, which are jails. Jails are basically what the kids are calling containers these days. VNet jails have their own IP stack. We'll cover those in a little bit more detail when we talk about how I've wound up testing all of these changes. But essentially, say that you have a nice server machine, a nice big server machine, many cores, lots of memory. You run some virtual machines on that, you want to connect those virtual machines to something. So you take the interface, the tap interface that comes out of those virtual machines, you bridge them together, and now they can all talk to each other. Just as if those would be physical machines and you plug them into a switch, that is exactly what you can do with IF-Bridge there. And at that point, your virtual machines can talk to each other, but not to the internet, so you get to decide how you want them to be able to access the internet. You could plug the internet cable into your switch, that is, bridge your LAN interface from your hosting machine into that IF bridge on your machine, and then they can all just switch out to the internet. Or you can route and optionally do that between them. It's entirely up to you, full flexibility. The operating system gives you options, it's up to you to decide how you want to do it, of course. Given that use case, keep that use case in mind as we go through this, because that's basically one of the things that we care about and why we care about performance. I've already mentioned, there's one, I've already mentioned performance, so clearly that's the problem that we're trying to solve here. Because if there were no problem, there wouldn't be a talk, and that wouldn't be terribly interesting. So what's the problem? The problem is that it's slow, or at least not as fast as it could be. I've got some output here from a test setup. Every other line, the first line, the third line, the fifth line, and so on, are packets that we generate. So imagine we have a test setup here with two machines. Both of them have two network interfaces, and those interfaces are linked to each other. On the test machine, we configure a bridge, and we bridge interface 1 and 2 together. On the packet generating machine, we generate packets out one interface, and we see how many of those packets make it back to us on the other interface. So that's what we see here. First line is the number of packets we send, second line is the number of packets we receive. We can send out 27 million packets per second, which is a respectable number of packets, but we only receive 3.6, 3.7 million packets per second, which means that there are about 23 million packets that get lost along the way. And they get lost because our test machine is simply not fast enough to handle all of these packets. Before we go into details about why this happens, quick note about the packet gen tool. Packet gen is a tool that generates packets, which may not surprise you. But it's a very interesting tool because it's based on top of NetMap, which is a framework for, as they describe themselves, extremely fast and efficient packet I/O for user space and kernel clients. It's something that works on FreeBSD, Linux, and some Windows versions. Obviously, we only care about FreeBSD version. But it's a great tool for generating many packets. And you can see here 27 million packets per second. This is a fairly substantial number of packets. It turns out when you're doing network performance testing, the first tool you are typically inclined to grab for are things like iperf3, and they're nice, but they tend to have a lot more overhead. They tend to struggle to generate very many packets. And it's very difficult to diagnose your performance problem if you're running into a different performance bottleneck. If you can't generate enough packets, you can't properly stress your test machine, and you can't really figure out where your problem is. In this case, PacketGen generates many packets, and we can clearly see we're not receiving as many packets as we would like. So that means we've established that there is a performance problem. Now, of course, we're interested in knowing in which part of the stack is this performance problem. Is it that we simply can't receive these packets? Is it that we can't process them fast enough? Is it that we can't transmit them fast enough? To do this, we've got more shiny tools. In this case, PMC-Stat. PMC-Stat is a FreeBSD tool that lets you enumerate hardware performance monitoring counters. Your CPU, most CPUs, because you have different architectures and all that, but your Intel CPU has a bunch of performance counters built into it, which means that you can do performance measurement with little overhead. And that's nice, because often when you use other tools, I'm sure those of you who have tried to run code under a debugger have noticed that it's much slower running in the debugger than it is running natively. FreeBSD has a bunch of other nice tools to do debugging like this. dtrace is very nice, and that was obtained from the Solaris people. But the downside of things like dtrace, like blockstat, like a whole bunch of other tools, is that they have a fairly substantial performance overhead. Now, when you're doing this debugging in a test setup, the fact that it's slower isn't too much of a problem, but it is a problem that it has a tendency to skew your test results. That is, you may end up seeing performance bottlenecks that are related to the tool that you're trying to use to diagnose a performance bottleneck rather than the real problem. Because PMC-Stat uses hardware performance counters, you tend to not have that problem. So the results of this are presented here in a flame graph. If I recall correctly, flame graphs are something that was invented by Brendan Gregg, who fairly literally wrote the book on performance benchmarking and analyzing performance issues. I would recommend that book to you all. I should also recommend it to myself, because I have to confess I haven't actually read it myself, but the man clearly knows what he's talking about. Anyway, we have a flame graph. How do you interpret this? Essentially, the width of a line indicates how much of our time we spent in that particular function. Going upwards in the graph, what we have is essentially a call stack. So if we skip some of the boilerplate things from FreeBSD's interrupt handling code, what we see is that we have the T4_inter, which is the interrupt service routine for the network card that we happen to be using for this test. And this calls into service IQFL, which calls into ether input, which is the Ethernet input handling code, which dispatches, which goes into ether NNH input. I'm not going to go into too much detail about how things work in the rest of the FreeBSD network stack, but that calls into bridge input. So bridge input sounds a lot like it's related to our bridge. Bridge input, we can see, also calls into way off into the right bridge forward, which does a bridge in queue. So that sounds very much like we've received an input packet, we've decided that we need to forward it, and then we enqueue it for transmission. And that makes sense because bridge enqueue calls into CXGBE transmit, which is a transmit function for our particular network card. So that's all good, except that we've got this other function here, and we seem to be spending the vast majority of our time there. Something like, eyeballing it 60% of our time in __mtx_lock_sleep. While sleep is a wonderful thing for humans, computers should be working. They shouldn't be sleeping when we expect them to be forwarding packets. So this seems like a fairly good contender for this is related to our problem. Next step, obviously, is understanding what this function means. Well, it turns out MTX is short for mutex, and us programmers were terribly lazy people, so saving ourselves 2 keystrokes is critically important. So we type it MTX rather than mutex. Mutexes, what are they for? They provide mutual exclusion. Great, that doesn't really enlighten. What they're for is to protect our data structures. So while we're processing packets, we have in memory some data structures that represent our bridge, and that keep track of things like what interfaces are a member of this bridge, and this particular MAC address, which interface should I send that out to? Things like that. We keep those in internal data structures. The problem is, or the reason that we have mutual exclusion is, say that we have a machine with 2 cores, a very slow and cheap machine, because these days you get many more cores than that. But let's, for the sake of the argument, say 2 cores. One core is busy updating some of those internal data structures. Say that we've decided to add an interface to the bridge, or we've learned a new MAC address and we're putting that in our list of, these MAC addresses go out of this interface, these MAC addresses go out of that interface. It turns out that while we update those data structures, there are transitory states, so states in between 2 valid states. And if, while we're doing this update on one core, the other core tries to run through the list of interfaces that we have, member interfaces of the bridge, or it tries to look up a destination, it has a MAC address and it needs to figure out which interface to send it out of, it's possible for that other core to read the data structure while it's being updated, while it's in a temporarily invalid state. And if that happens, computers are very literal minded. We're going to end up doing things that we don't want to do. We're going to dereference a pointer to memory that's not initialized. We're going to dereference a pointer to memory that simply doesn't exist. We're going to read incorrect MAC addresses. All sorts of bad things can happen. And usually this would manifest as kernel panic, and the system just completely stops forwarding packets. And that's not terribly useful. We prevent this by the process of mutual exclusion. We exclude other cores from accessing the data structure while our core is busy updating them. That's what these mutexes provide. And that's essentially how the bridge protects itself. And that's great. The problem is that the bridge is, or before my work at least, the bridge was fully covered by these mutexes. And essentially the result of that was that it doesn't matter how many cores we have, only a single one of them can be doing useful packet forwarding work at a time. And then obviously, we've paid for shiny, expensive network hardware that will very carefully make sure that some parts of our packets go to one core and some parts of our packets go to another core, so that the work is equally balanced between cores. We spent money on an expensive CPU that has 20, 30, 40 cores that can all do useful work, and then our software goes, core 1 will start processing this packet, and all of you other cores wait while I'm doing this. Kind of a shame and a waste of money, clearly. So how can we do better? Well, it turns out that mutual exclusion is not the only way, or mutexes are not the only way we can do this. You may have noticed that I was talking about it being dangerous to access those data structures while someone else is updating. But the majority of the time, when we look at those data structures, we're not going to update them, we're only interested in reading them. So if we invent a lock, and well, we don't have to because somebody else did this a long time ago, but we have locks called RWLock, or a read-write lock. And they allow multiple readers to access the data structure at the same time. Because they're all only reading, they're not going to encounter any invalid transitory states. So we can have 40 cores reading that data structure at the same time. Excuse me. It's only when we want to update it that it becomes a problem. We can only have a single writer at a time and no readers while this is going on. But because updates are much rarer than reads, this already improves matters greatly. And in fact, I prototyped a solution like this and got fairly substantial improvements in throughput. Turns out we can do even better because the RWLock expects to have a very large fraction of its updates, of the times that it gets locked to be write locks. We also have an RMLock, which is a read-mostly lock, which is optimized for, we expect to have many more readers than writers. And it does actually have a significant performance impact. So that's great, but it turns out that there's an even better way, and that's the epic system, which we obtained from the Concurrency Kit people. Concurrency Kit is a toolkit of locking primitives and related code for concurrent operation, concurrent access to data structures. That's been integrated in FreeBSD, and some other people, people much smarter than me, have done a lot of work to make the network stack use this. My work is essentially to make the bridge also use this. So what do we get? One of the things we get is a new list data structure. So a lot of the data in the bridge is kept in linked lists. Node 1 points to node 2 points to node 3 and so forth. And the concurrency kit lists are special in that we can read them without taking any locks whatsoever, and this is perfectly safe. As long as we guarantee that only one core at a time will perform updates. They actually describe this in their comments as, it's safe to use for each in the presence of concurrent modifications to the list. Writers to these lists must, on the other hand, implement writer-side synchronization, which means we can have a single writer, but while it's being written to, we can have as many cores as we like reading from this list at a time. The distinction with the RW or RM blocks is that when they were writing, there couldn't be any readers at the same time. So this sounds like it would be even better. We use this in Bridge, I think I've already mentioned, for three main data structures. IF-list, which is the list of member interfaces of the Bridge. The RT hash, which is the list, hash and list of MAC addresses, which tells me that MAC address A goes out of interface 1. And the span list, which is our list of mirror ports. We need to copy all data to this interface and send it out there. And for these three lists, there are three relevant scenarios that we need to consider. How do we carefully manage this so that the epic system will work, so that we can safely access and update these data structures? First one I've called iterate, which is the read case, is we run through the list of entries, looking at them, potentially using some of that data to process our packets. We can also have to insert new items, that is, we add an interface to the bridge, or we have learned a new MAC address and we keep that in our RT hash. And then finally we have the delete case. We remove an interface from the bridge, or much more commonly, one of our MAC address entries has timed out and we're going to remove it from the list so we don't use it anymore. The iteration case is the simplest case, really. Because we don't need to take any locks, well, we don't need to take any locks. We can read with as many cores at a time as we like. The only thing that we need to do is we need to indicate that we have started using these data structures, which we call being in epoch. There are macros to do this for us. What we will see in code is net epoch enter, net epoch exit, to indicate here we start using the data, here we're done using the data. Those macros, they never block. You can do this at essentially any time with as many cores as you like, completely independent from modifications that might be going on at the time. There's nothing to stop you. There are no roadblocks, no speed bumps. You only keep track of, I have started using the data and I am now done using the data. We do need to remember that this is a read access, so we can read the data structures, but we can't safely modify them. Because of course, some other cores might also be reading the data, and if we go and modify it while they're reading it, bad things could happen. But, important to remember, we can read with as many cores at a time as we like. Second scenario is we insert a new entry. In this case, we must hold a lock. We must prevent other cores from inserting or deleting data at the same time. In the bridge, I've chosen to reuse the pre-existing bridge mutex. We already have a lock. All we've done is narrow it, where we used to take the lock every time we access any of the bridge data structures, be it for read or for write. We now only take the lock when we're going to write to the data structures, and we don't take it when we read. We take this lock because, remember, there can only be one writer to the CK list at a time. Second constraint is we must remember that the very instant that we insert an entry in the list, another core can start to use it. So that means that before we insert that entry in the list, we must fully fill it out. Say that we have our RT hash example. That is an entry that indicates for this particular MAC address, use this interface. So this structure has essentially two relevant fields. We must fill out both the MAC address and the destination interface before we insert it in the list. Because if we didn't, say that we did not fill out the pointer that says, use this interface for output when you encounter this MAC address, and we insert it, it's possible that a packet for that MAC address arrives while we're doing the insertion. It does the match on the MAC address. It looks at the pointer and goes, I will use this interface to transmit the packet. That pointer is not filled out. We dereference a pointer to null or an invalid pointer, and then bad things happen. If kernel panics, your machine stops forwarding packets, and people become very unhappy. It's not very difficult. Just remember, fill out the data structure fully before we insert it in the list. And then finally, when we want to remove an entry, and this is the tricky one, again we must hold the lock, just like with insertion, because only one writer to the list at a time, and removing entries from the list counts as writing to the list. The problem here is we are removing something from the list, but other cores could be iterating through the list at that time, could be reading that structure, could be trying to use that data. How do we make sure that we don't free that memory that we don't start to reuse that memory that some other core could be using when we're deleting it. The solution to this is that we defer the delete. We will remove the entry from the list, but we will not actually free the memory until we're sure that nobody is using it anymore. And that's essentially what the epoch mechanism does for us. Because we track when readers start using the data and when they stop using the data, we can know for sure when no other core could be using this particular data structure anymore. So the order of operations here is we remove the entry from the list, but we don't actually reuse the memory for anything. So the structure itself remains valid and remains usable. So imagine that we have a core that is going to read our data structure. It enters epoch, it says, I will start to use this data. It runs through the list and it finds the entry that it's interested in. And it goes and looks at the MAC address, it goes and looks at the network interface. Simultaneously, a second core removes that entry from the list. So we don't know the relative timing of events. It's possible that we've removed it from the list before the iterating core, before the reading core saw that entry, and then we could basically safely remove it because the other core is not using it. But we don't know that. So we assume that the other core is using it until that core hits net epoch exit, which tells us that, hey, I've stopped using this memory, or I stopped using this data. And at that point, that's what the epoch system provides for us. It keeps track of when cores enter and exit epoch sections, and when we know for sure that no other core is still using this data. So we have what we have the net epoch callback for. We register a callback, and when we know that the data is not going to be used anymore, it gets called and we can free the memory. So here, the important thing to remember is that between step 1 and 2, after we've removed it from the list, it's still possible for someone else to be using it. Let's look at a little bit of code here. 2 functions. Because software developers are weird, we start reading from the bottom. Bridge RT node destroy gets called to remove an RT node. An RT node is essentially use this MAC address goes out of this interface. So what we do first and foremost, well, we assert that we have the lock. Because remember, only one writer to those lists at a time, we must have the bridge mutex to prevent other cores from updating the data at the same time. First thing we do is remove those entries from, remove the bridge RT nodes from the list. It actually is tracked in 2 lists for reasons of performance, but that's not actually relevant here. We update some counters while we're at it, and then we register our callback. Net epoch call, bridge RT node destroy callback, _ CB for callback. We give it a context pointer, which tells it, lets us figure out which entry we were trying to destroy when this callback gets called. Once this function finishes, we can release the lock, and someone else some other core may decide to remove an entry as well. Take the lock, do the same thing, register the callback. Eventually, after not too very long, in fact, other cores will be done, will have exited their net epoch sections, and we know that the data is no longer in use. And then this function, the bridge RT node destroy CD callback, will get called. We know that the data is no longer used, so we can free the memory, and once we free the memory, it can potentially get reused. And that is essentially the whole notion behind how the epoch system works and the changes that we made. The question now becomes, did this help? Because it's performance work, you need to test it because it's often non-intuitive. Did this actually help? Did this make things better? It's also commonly the case, or often the case, that you remove one bottleneck and only then discover the next bottleneck. So let's go and measure. We do the same PMC stat dance to get the performance counters to figure out, where is our bottleneck now. So what do we see? We still have our interrupt handling routine. We have ether input, which calls into NetISR dispatch, ether NH input, bridge input. In bridge inputs, we now no longer spend time sleeping, waiting for other cores to be done. We spend most of our time on bridge forward. So the thing here is that just because this is wider doesn't mean that bridge forward, we spend more time in bridge forward now. That doesn't necessarily mean that bridge forward got slower. This is a relative representation. We spend more of our time in bridge forward than we used to. We spend more of our time in bridge forward than we used to, not because it's slower, but because we're forwarding more packets. So when we look at the actual measurement results here, we see that we're still sending 27 million packets per second, but we're now receiving 18.6. Before this change, that was 3.9 million packets per second. 3.9 to 18.6, I think we can all agree, is a fairly decent performance improvement. For those of you interested in more details on this, there is a presentation by the Concurrency Kit people about how this epic thing works. We can also look at the actual patch. I wound up doing several different patches in different steps. First couple of patches being some general cleanup, but this is the main patch turns the bridge from using a single mutex into using the epic system. We get rid of a bunch of really nasty locking complications for the bridge. We wound up adding some epic context pointers, and then we have, let's see if we have a good example here somewhere. Yeah, when we look up members, we iterate through a CK list. We must be in epic. Net epic assert is just an assertion. We don't actually enter the epic here, we only say that if you are here, you must have entered epic. And then we have some examples, so yeah, there we go. Bridge delete member, when we remove a member interface from the bridge, we used to have bridge locked here, but actually, and then immediately free it, but what we do now is we don't free it anymore, but we register the callback to free it later. Later on, when we know that nobody's using the entry anymore, we will bridge delete members called CB, where we do this, which is the deferred delete of that entry. For those of you interested, feel free to go and take a long look at this patch. While I'm going on about this, I have an entire separate talk about how we can use VNet to test bridge code. But during this work, I want to test that this still works. So I wrote some automated tests for this. Basic transmit packets, test that spanning tree works, test the ability to add static MAC entries. That is to statically configure that MAC address 1, 2, 3, 4, 5, 6 goes out of interface 1. Testing our mirroring ports. This was an amusing bug that had been open on the bridge for a long time. And if the FreeBSD Mozilla wants to cooperate, there we go. It used to panic with this message in specific configurations, fortunately not always. But this happened when we tried to add an interface to the bridge, and this is in configuration where the bridge takes over the MAC address of the first interface that we add to it. So we enter the IOCTL handler, that is when user space tells the kernel add this interface to it. We handle this in the bridge, we add an interface, and adding the interface causes us to change our MAC address, which causes the ARP code to send out an ARP reply message over our interface, which gets transmitted out over the bridge, which requires us to take the lock. Only we've already taken the bridge lock in this function. So we try to take a lock that we already have, and then the kernel becomes unhappy about this because it says, we've recursed on a non-recursing mutex, which is, we've tried to take a lock that we already have, and that's bad. And this is now fixed because while we still take the lock here, we don't need it here to transmit. And so this bug was sort of incidentally fixed. The reason I'm looking at this bug is because I can show you the test case I added for this. And this is all of it. So this is just boilerplate, add this test case to the list of test cases. There's some boilerplate startup, we add a description, we point out that we need to be root to run this test. And then what we do, some more initialization code, we create a bridge, we create an interface, we create a jail. This jail will have its own IP stack, and we will give it a bridge interface and an interface to put into it. Configure MAC inheritance because we need that to trigger this bug. Add an IP address to the bridge, and add the interface. And this, without the bridge changes, used to crash. So we don't actually need to verify anything, because if your system panics, it's very obvious that your test failed. I point to this one because it's 1, 2, 3, 4, 5, 6 lines of shellcode to write a test for a kernel bug. So that's particularly useful. There are, you can see there are a bunch of other tests. Some of them are slightly more complicated to implement, but only slightly more complicated. And having these tests is incredibly useful. I wound up writing the majority of these tests before I did the implementation. And then while I was doing the locking change, I could run these tests, and I didn't cover all of the functionality of the bridge, but it covered enough that I found a fair number of crashes just using these tests. That basically covers everything. So if there are any questions, now would be an excellent time. I will also put up these links. There is some more information. The FreeBSD Foundation wrote a blog post about this project, and the FreeBSD Journal has an article about this bridging work as well. So if you're interested in rereading something, you can find this online. I will give the organizers a copy of my slides so they can put them up, so you don't have to go and furiously write down these links. If there are any questions, please go ahead.
I'll attempt to restate your locking scheme change to see if I got the gist of it. Is that okay? So before your work, all read and write access to the bridge code is governed by a single mutex. You apply what Paul McCamey of IBM and the Linux people would call recopy object to the new bridge code locking scheme. After your change, all concurrent writers are still governed by a single mutex. The lock protection between one writer and potential concurrent readers is that before publishing a pointer, the structure pointed to, the memory order between the structure pointed to will be filled out first. This would be referred to as a memory order consumed in the new C11 memory model. The tricky case is the deletion case, where you're using the epoch subsystem as a four-man Scottish collector, and you're only calling free once all references to the object has been removed from the system. Is that roughly correct?
That is entirely correct. I see only two possibilities. Either I've explained this extremely well, or you are very clever.
similar stage to that sensor. But you would expect them also very quickly as well. I would love to know what your reaction is. And then the test case looks pretty amazing for its coverage.
If you're interested in learning more about test code, I've done 1 or 2 versions of my talk on firewall testing in FreeBSD. If you search for my name on YouTube, you should find it immediately.
Hi, Kristof. I wonder if there's anything you need to do about the CPU reordering or memory barriers, or does the macro from Concurrency Kit handles that for you?
Concurrency Kit macros, the Concurrency Kit code rather handles this for us.
All right, thank you.
Is there any questions? Alright, Kristof, I think there is no questions so far, or people are just shy. Okay. So I'm not sure Kristof can hear our claps, but let's still do it. Okay,
Thank you very much.
So go first. Okay. Let's call it a day. Thanks everybody for joining. 好，那就谢谢大家参加今天的那个 talk。那如果本来是说那个明年的 HLSD 抗会在台湾办啦，然后 Kristof 应该也会来，可是大家都知道那个现在疫情还是就是除了台湾是平行世界以外，其他地方都不知道怎么办，所以现在我们也很烦恼，到底要不要继续办下去啊？那 anyway 就是跟刚刚一样，就是有任何问题，就是网络上在讲。那 Kristof 他非常的 active， 也很热心，所以如果找不到他的话，也可以反正先找我，我再想办法帮大家这个 run。那就是对吧？还是要说，就是今天每个 talk 时间都很有限，然后可能大家那个实作啊什么的都还没有办法做的尽兴。不过先给大家一个开始，然后有什么问题就是我们网络上在问，或者是就是在办实体的聚会。那反正现在也都不能出国，反正所以大家应该比较有时间在台湾再做聚会。好，那谢谢大家。